Okay, all right, let's start. So today here is today's outline. Like before, we will go through some announcements first. And today we are releasing the not the specifications, but the setup guide for assignment 2. And then we will have a quick recap of what we have learned on Monday. And then we will learn something about the relational design theory. So here, the first announcement is that the specifications will be released later this week, and the due date would be on Wednesday of week 10. And the purpose for this assignment is for you to practice Cycle PG2. Actually, it is set to be practicing the Python module, but in the end, you are still writing SQL queries. So it's essentially a practice for SQL queries. And of course, because it's a Python module, you will be using Python for this assignment. And you should do it earlier because you can, if you encounter any questions or problems, you can ask them earlier, so they could be so we don't need to rush to solve those problems. And another reminder here is, if you would like to post your assignment code, you should use private posts. And the second announcement is quiz 4. The due date is this Friday, tomorrow. So you just try to do it. And the third announcement is the Thursday session is to be shifted to 11 to 1 today on Thursday, but it's not officially confirmed by the admin yet. So, however, one of our tutors, he's willing to do double sessions, so he's also there available for help from 11 to 1 on Thursdays. So that's about the help session. And wait, my computer stuck. Oh. And for assignment 2, could you make a guess which database will we use here? And this assignment was complained as being too hard, the database we're gonna use. But I think it's an interesting database, so let's use it again. And I will explain to you why it was complained as hard. And the database is about Pokemon, so it's a Pokemon database. And as you can see, this is the ER diagram of this Pokemon database. So you can see there are a lot of entities, there are a lot of relations. It's much more complex than the movie database. But although it is the ER diagram looks more complex, it's not hard to understand, because I believe you must be familiar with Pokemons, right? So no. okay, but they are quite intuitive, and there are not many very complex concepts here to be used. And this is about the relations between different entities. And here are all the attributes for each entity here. And in total, we have 9 different types of entities in this database. And the most the entity with the most attributes is just the Pokemon. And we could have some composite entities here as well. For example, the ID of the Pokemon is a composite entity, and the levels here is also a composite entity attribute. So here are all the attributes. This is available on Web CMS. You can view them at any time you like. So we have released the schema and data dump and all the diagrams on Web CMS. You can access via this link. And what I would suggest to you is, because we are not releasing the questions yet, the specifications yet, what I would suggest to you is to set up the database earlier. Because for assignment 1, we were receiving setup problems on the last day of the assignment. So that's very bad. So you can't finish everything on the last day. So what I suggest is, since we have released the setup guide, just set up the database earlier. And another thing is, we will provide you less questions than assignment 1. So basically, we will give you 4 or 5 questions for this assignment. So you don't need to worry that much. And as I just mentioned, this database was complained by the students as too hard. And it was not because of the complexity of the ER diagrams of the entity relations. It was complained because of another thing, because of how the questions were designed. So a person, let's think about this case. A person who can speak multiple languages is called what? Is called a polyglot. Yes, a polyglot. And programs involving multiple programming languages are also called polyglot programs. And we need to be careful when we map data types across different programming languages. So here, the program we create using the Python module CyclePG2 is a polyglot program, is essentially a polyglot program. It involves both Python code and SQL code. So there are data transferred between these two types of languages, and they could have mismatches. So we need to be careful when we do data conversion across different languages. And it's especially important for floating point numbers, because you can either do the calculation on the Python side or on the SQL side, and they will produce you floating point numbers with different precisions. And what we did for last time was some students will do the calculation on the Python side, and some students will do the calculation on the SQL side, and they will generate different results because of the precision issues. So that's why they are essentially doing the correct thing, but they are generating different results, and it's very hard to assess. So that's why it was complained. And this year we will avoid this issue. We will avoid the usage of floating point numbers in this assignment too. And I hope it won't be that hard this time for you. So that's all about assignment 2. And another thing is talking about doing things on which side of the code. You should, for this assignment, you should try to do data processing as much as possible with SQL instead of Python. So some students, they would just use, you can use the cursor to select, to fetch all data from all the tables and do the data processing always with Python. So that would be very, very slow, because Postgres is highly optimized, and using Python is a slow language. It's easy to use, but it's slow. Its execution is very slow, and because it's an interpreted language, it's not a compiled language, so it's slow. And SQL and Postgres does have a lot of optimizations. So instead of, it's indexing all the data. So it's actually very similar to search engines like Google. So when you Google something, it's not Google crawl all the internet and do a stream match for whatever you have searched. It's not a simple stream matching. Google is indexing all the data. So it's similar for Postgres. Postgres is helping you to index all the data stored via the tables. So it's very, very efficient to do data processing. So that's why you should try to do data processing as much as possible on the SQL side. And the Python is just an auxiliary code here. So that's just a reminder. And now let's come to a recap of what we have learned in the last lecture. So in our last lecture, we have learned Python. So we have relearned Python. I hope it's a relearning process for you. And Python, so what we have covered are the basic syntax of Python. So I hope you are familiar with this. So Python is made up of all those indentations. And if you want to add a comment in Python, you should use the hashtag. And we have also learned some expressions and operators in Python. And we also learned some data types in Python. And we also learned the definition of functions. And we also learned that Python code could accept command line arguments. So do you still remember how to process command line arguments? So via which variable? Yes, sys.argv, yes. You should import sys, the system module first, import sys, and use sys.argv to access the command line arguments. So that's all about Python. And we also learned the data the module called cyclepg2. So we learned how should we use this in our Python code. What we should do, we should import this module first, and then we build up a connection, and this connection will give us a connection object, and we can do a lot of things with the connection object. And one of them is close. Of course, we need to close the connection properly. And another thing is we can create a cursor through the connection. And with this cursor acts as a handle for transmitting data between SQL and Python. So we can use this cursor to execute SQL queries. And we can also use cursor to fetch the results returned by the SQL queries. So there are 3 different types of fetching. So do you still remember them? Fetch one, yes. Fetch one, what does fetch one do? Yes, next. It's not just returning one, it's returning the next. So it's actually moving forward. So that's fetch one. And what else do we have? We have two other types of fetching here. Fetch all, yes. Fetch all will give you all the results, all the tuples returned by the SQL query. And what else do we have? Yes. Yes, the next n number. Yes, the next n numbers. Yes. So we have 3 types of fetching here, and And we also learned how to invoke PGSQL functions. So there are actually two different types alternatives to invoke SQL functions via a cursor. So do you still remember them? So what is the first type of invoking an SQL function? Yes, you can execute a query, and that query should be select from the function. And what else? Yes, call procedure. There's a special function provided by COMP3311 called call procedure. So we can use cursor.call procedure followed by the name of the function and a list, which is the parameters provided to that SQL function. So that's all about what we have learned for COMP3311 in our last lecture. And as you can see here, COMP3311 is just an interface for Python to interact with Postgres. So what you will be essentially doing for your assignment 2 is still writing SQL queries, still writing proper SQL queries. So that's about the recap. And now we have learned what we have learned so far are how we do data modeling. We have different types of data models. We can use ER models, we can use relational models, and how do we map between ER models and relational models. And we have learned SQL as well. So most of them are actually engineering related. And now let's touch some of the theoretical part. So what we will learn today are the redundancy in relational design and functional dependencies. So why do we learn this relational design theory here? So the aim of studying the theory here is twofold. So first, we would like to improve our understanding of relationships among data. And then we also want to gain enough formalism to assist practical database design. So this is why we learn this. And what we will learn here is the basic theory and definition of functional dependencies and the methodology for improving schema designs. So we have the theoretical guide to help us to do proper designs. And functional dependencies here are used to describe relationships between attributes within a relation and or across different relations. We will learn that later. And it has implications for good relational schema design. And we will see that later as well. So talking about a good relational data design. So what should it do? It must be able to capture all the necessary attributes and associations. And it should capture all the information with the minimal amount of stored information. So we can always store additional information in order to capture all the attributes, all the associations, all the relationships. We can use excessive amount of information here, but a good design should store the minimal amount of information. And minimal stored information means no redundant data. And in database design, redundancy is generally a bad thing here because it could cause problems for maintenance. However, redundancy sometimes may give us performance improvement. For example, if we if we merge different tables into one big table, we could avoid join operations, and join operations is often time consuming. So that's one example for redundancy giving a boost for performance. And what else can you think about redundancy could help? Another example here is materialized view. So a normal view is just a reference to the actual stored table. And a materialized view is actually like a table. It is also stored in the database and is occupying some space in the hard disk. And it could be thought as some kind of redundancy here, materialized view, because they are essentially storing some duplicated data as the actual tables. But they can help to improve the performance, because for normal views, what they will be processed by the database is to be converted into actual queries. When we run the query on that view, it will be converted into query on the stored tables. But for materialized view, we are actually using it as a normal table, so it would be much faster. So in some cases, redundancy may give us performance improvements. So this is the mechanism here. However, in general, it's a bad thing, and we will show you with an example of why redundancy could cause problems. So let's consider this table here. So this table is a table capturing the data for different customer accounts and branches. This table is used for banking. And here, a key concept here is called asset. And asset is used to keep track of the total amount of money stored in a branch. And the balance is the money remaining for an account. And as you can see here, this table now is very consistent. There's no inconsistency here. However, there are some redundant data. So we can see that one branch could appear multiple times in different tuples here. This is kind of redundant. And let's see why this redundancy could cause problems. And the first thing is careless update will cause problems. So let's say we add $300 to the account of A113. And since we are modifying the amount of money in for a particular account, we should also update the assets value for the branch, for the corresponding branch, because the assets is a sum of all the balances related to that branch. So we should also add 300 to the assets here. However, since we have redundancies here, this round hill branch for A113 is not the only appearance of this branch here. So we have another appearance for this branch in our last row. And let's say we don't have a mechanism to maintain the consistency here. So we need additional measurements to keep them consistent. And let's say we don't have any additional measurements, so we just update the single line of a single tuple here. Then this could cause inconsistency. And this is only, there are only two accounts here in this example, but actually, as you can see, the assets is much larger than the balances than the balances here. So there could be a lot of tuples to maintain here for this update. So it could be very troublesome. So this is the first example of why redundancy could cause inconsistencies. And the second one is when we do insertion, it could also cause problems. For example, let's say we create another account called A306, and this account has a balance of 500. And how should we modify the assets here? So because we have discrepancies here, we have two different values for the assets here. So should we just use the last one or the first one? So we don't know here. So there could be inconsistency as well in this case. And the last one is when we do deletion, it could also give us inconsistencies. So let's say we delete the account A101. So it will affect, first it will affect the assets that of the affected branch. And the worst case is if this account is the last account for that branch, we will totally lose the information of that branch about the downtown branch here. So let's assume this A101 is the last account for the downtown branch. And we remove this account, we are removing the information about the branch as well. So we could lose information here in this case. So deletion could also cause problems for redundancy. So as you can see, redundancy could cause some problems or anomalies. And there are three different types. So the first one is called insertion anomaly. So when we insert a new tuple or new record, we need to check that the branch data is consistent with existing tuples. So in our previous example, so we could encounter insertion anomaly if we don't handle them properly. And redundancy could also cause update anomaly. So in this example, if a branch changes address, we need to update all the tuples referring to that branch, and there could be a lot. And the last one is deletion anomaly. And this example here is what we have discussed just now. The worst case is if we remove information about the last account for that branch, all the branch information will be lost. So this is very bad. And insertion or update anomalies can be handled via triggers. And you will be using triggers for your quiz 4, so don't forget to do your quiz 4. But this requires extra DBMS work on every change to the database. So assume you have created a lot of triggers for your database. So almost every transaction or almost every query would trigger some triggers, and your database will execute very slow when there are multiple users or multiple connections. So we should avoid using, actually, although triggers could solve the problems here, but we should avoid using triggers as much as possible. So we need to deal with this. So what we could do is we could solve the problem from the design level. So we could design the database to avoid redundancies. So that's why we need to learn about the relational design theories to provide us some guidance from the theoretical aspect. So to avoid these kinds of update problems, we need a schema with minimal overlap between tables. So we need to know the relation of attributes across different tables. And each table should contain a coherent collection of data values. So this type of schemas will have little or no redundancy. And we have learned how to map ER diagrams into SQL models. And ER to SQL mapping tends to give us non-redundant schemas. However, it doesn't guarantee no redundancy. So can you quickly think of one case for redundancies here? From the conversion of ER models to SQL. Can you think about one example here, which could give us redundancies when we do the conversion? Excuse me? Inheritance, yes, very. That's very fast. And actually, inheritance will sometimes give us redundancy. So we have three different ways of handling the mapping of inheritance. So the first two styles of mapping inheritance is we could use a separate table for each one of the subclass. And the first one is the relational style, which is to separate which is to create a separate table for each one of the subclass and use foreign keys to link the data between the subclass and its parent class. That's the first style. This one will normally give us no redundancy here. The second one is we could also create a separate table for each subclass, but this time each of the child class will have all the attributes from the parent class stored in their table. So this time we could have some redundancies here. And the last style is to use a single table to hold all the attributes from all the subclasses or parent classes from this inheritance relationship. We will put them into one table and allow some values to be null, and this will also give us some redundancies here. So because some values are null and some values are not needed for some subclasses, so that's why ER to SQL mapping does not give us a theoretical guarantee of no redundancy. So now let's learn an important. So we will try to solve this from the theoretical aspect, and now let's try to learn a concept called functional dependency first. And before we learn that, let's have a 10 minutes break and And I didn't forget to bring the snacks, so you can grab some here. So, okay, let's have a 10 minutes break. All right, let's start our second half. So we will be learning an important concept here called functional dependency. So first, let's go through some notations or terminologies which will be used a lot. So here's a list of terminologies. So the first one is attributes. So we use uppercase letters from the start of alphabets, so as to denote attributes, and we use the concatenation of attribute names as the set of attributes. For example, the X is a set of attribute which is made up of A, B, C, and D. Y is a set of attributes which is made up of E, F, and G. So this is how we denote set of attributes. And for relational schemas, we use uppercase letters denoting the set of all attributes. And for example, we use the uppercase letter R. And for relation instances, we use lowercase letter corresponding to the schema. So in this case, we use R followed by the parentheses and uppercase R here as the instance of a particular relation. And for tuples, we use lowercase letters. For example, we can use T, T prime, T1, U, and V as tuples. And for attributes in tuples, we use the square bracket to indicate the set of attributes inside a particular tuple. So for example, T A, B, C, D means the set of attributes A, B, C, and D inside the tuple T. So here are all the notations, but you don't need to remember them now. We will be using them a lot, and you will kind of memorize all the notations here through the usage of these notations. So let's first come up with a definition of functional dependency. So a relation instance R satisfies a dependency X determines Y if for any T and U of that instance, so for any two tuples of that instance, so you can refer to the list of terminologies here to see what are the what's the meaning of these letters or notations. So for any two tuples from that instance of relation, if the set of attributes X equals to each other across the two tuples, then Y would also equal to each other across the two tuples. Then we will say X determines Y. So in other words, if two tuples in a relation agrees in their values for the set of attributes X, then they must also agree in their values for the set of attributes Y. We will say that Y is functionally dependent on X. And of course, X and Y here are sets of attributes, and their attributes could overlap. And it is very trivial. It's trivially true that X is functionally dependent on itself. So because if two tuples have the same value of X, then they must have the same as value of x, right? So this is kind of very trivial, and we can also say that, okay, this could be also read as x determines y. So our y is functionally dependent on x. So the single arrow here denotes functional dependency, and the double arrow here is the logical implication, which could be translated into natural language as if then. So if something here, then something here. So here is the formal definition of functional dependency. So this reminds you of what concept we have learned before. So x could determine the value of y. So if x is fixed, then the value of y are the values of the attributes inside y are also fixed. So which concept can you think of for describing x? It's very similar to the concept of keys, because once the key of a tuple, or once a key is settled, then the rest of the values are also settled, are also fixed. So the concept is somehow related to keys, but we will learn more about this later. And here's an example. Let's try to practice of what we have learned. Here's an example from of movies, a movie database. So let's try to consider the following relation. So once we have fixed title and year, what else are determined? So let's say for two tuples, if their title and year are the same, what else attributes would also be the same here in this table? Studio, yes. Length, yes. So studio and length will also be the same if title and year are the same. So title and year determines studio and length. This is correct. So title and year determines star. Is this a functional dependency? Is this one correct? Why not? Can you give me a counter example here? Yeah. Yes. So the counter example is for King Kong. Actually, we can the third and the second and third lines or rows. The title and year are the same, but the stars are different. So this one is not a functional dependency. And here's something interesting on this slide. So actually this cross and tick are Unicode characters. So they are actually characters, but they are in Unicode, and different systems would render them differently. So this one is rendered by Google on Google Slides, and on Linux or on Windows, there could be different. They could be displayed differently. And do you know why this tick here is not in green color? Because red, we all know that red means is like warning or error. But why we don't use green here for this to indicate the correctness? So why does Google choose the purple color here? Do you know why? Actually, it's because it tries to make it user friendly for colorblind people. So some people they can't recognize or differentiate red color or green color. So that's why this one is purple. But in some systems, I believe in Linux is rendered as a green tick. So this Unicode character here. But anyway, I hope you are not distracted by this small thing here, and let's continue our learning journey. So let's think about a more abstract example here. So this time we have an instance of table R with the schema of A, B, C, D, and E. We have 5 attributes this time. And for A, we can see that for each row, the value of A is unique. And for E, for the attribute E, all the tables have the same value of E. So since A values are unique, what does it indicate here? So can A dominate or determine all the rest of the values here? Yes, right. Actually, yes. Actually, A determines everything else. And we can say that A determines A determines C, and A could determine a set of attributes as well. So this is about A. And what about E? Because all the values of E are the same across different rows. So what could we say here? Yes, yes. E, everything can determine E, or E is functionally dependent on all the other attributes. But you may notice there's a small difference here. So we can say A determines the set of B, C, D, E. But what about A, B, C, D determines E? Does it hold? Can we use A, B, C, D to determine E? Yes, it actually holds, but it's kind of redundant here because it's kind of weaker than any one of the relation here. So if D can determine E, of course C and D can be used to determine E. So you can get a feeling that okay, there are relationships between different functional dependency relations here. So some might be stronger, some might be weaker, and we can perhaps use someone to deduce some other dependencies here. So you can get this feeling here. And of course, we can, for this table here, we can make a lot of other observations. For example, since the combinations of B and C are unique, we can use B and C to determine the rest of the values. The combinations of B and D are also unique. Therefore, we can use the combinations to determine A, C, and E. And they don't have to be unique to determine other values. Since if C values match, D values will also match here in this table. Let's say if we have there are 2 matches here. So the first row and the third row, the second row and the first row, So we have two matches here. So if C values are the same, D values are also the same. Therefore, we could also say C determines D. But can we do it reversely? Can we say D determines C as well in this case? No, I see some of you shaking your head. So why not? Can you give me a counterexample here? Yes. D cannot determine C in this case because the last row here is D1 mapping to C3, and the first row is D1, C1. So even though the D values are the same, the C values are not. So D doesn't determine C. So we could have C determines D here, but D doesn't determine C. And we could also derive a lot of other dependencies here from this table. And how do we systematically determine all the dependencies? You may think, okay, there are a lot of dependencies we can extract from this table, but how do we systematically deduct all the dependencies? So in practice, we can choose a minimal set of functional dependencies as the basis. And from this basis, we can derive other functional dependencies using some inference rules. And this is very important for some problem domain information. So that's specific to the usage scenarios. And in the above examples, we consider the dependency within a one relational instance. However, in real world, in practice, we have dependencies across multiple instances of the relation. So we can do a very simple generalization of the formal definition for this functional dependency. So instead of TU from a particular R, we can add a keyword any here. So it's very simple. We just add one keyword here. So this will also hold. So the dependencies across different tables are normally useful for the real-world usage scenarios. And as we have covered just now, there could be potential links between different dependencies. And just now we showed you why there's a difference between the two set of dependencies, because some of them are weaker, some of them are stronger, and we can use stronger dependencies to infer or derive weaker dependencies. So there are relationships here, but how can we describe them? How can we use them to systematically derive all the dependencies from a given relation? So this is what we should think about. Can we think about how can we generalize some ideas about functional dependency? So let's first think about the most general rules or patterns here. So are there dependencies that would hold for any relationship? Yes, but they are normally very, very trivial. So if Y is a subset of X, then X must be able to determine Y, right? For example, Y is AB and X is ABC. Once the values of AB and C matches, of course the values of AB will match. So this is very trivial. So actually the dependencies that we hold for any relation are very trivial. So the second thing here we can think about is how can we formally define the dependencies, the relations of dependencies. How can we use one relation to derive another one? Actually, we can do that. We just have a feeling that there are connections that they could be used to derive each other. And yes, there are rules of inference which allows us to derive dependencies. And it allows us to reason about the sets of functional dependencies for a given relation. Sorry, I messed up with the animation here. And actually I forgot to add animation for these for the second and third, but let's go through this quickly. So the first set of rules are called inference rules are called Armstrong's rules. I'm talking about Armstrong. Who are you thinking about? Neil Armstrong, the one who the astronaut, but not that person. The person is called William Ward Armstrong, and he's a professor from the University of Alberta, and he's still alive, and he's almost as old as Neil Armstrong, but I think he's a bit younger, and he's the guy who came up with Armstrong's rules, and there are 3 rules here. So the first one is called reflexivity. So reflexing is like a mirror, right? So it means any set of attributes could determine itself. So it's very trivial, but it could be helpful for deriving some other rules. So this is very obvious, right? So if we fix the value of that thing, then of course that thing is fixed. So that's very trivial here. And the second rule here is augmentation. So if X determines Y, we can add values on both sides, and this determination or this functional dependency still holds. So we can use the second rule here is augmentation. We can add a set of attributes on both sides. And this is the second rule here. The third rule here is transitivity. So transitivity is very important because it could be used to derive some other rules. And it is like this. So if X determines Y and Y determines Z, then X could determine Z as well. So it's like the larger than or smaller than, so operators, they are also transitive, because if X is larger than Y and Y is larger than Z, and X will be larger than Z. So this is transitivity, and it's not very hard to remember, I believe. I messed up this animation again, but here are some other useful rules other than Armstrong's rules. The first one is additivity. So if X, so it is used to combine rules. If X could determine Y and X could determine Z, X will be able to determine the set of X, Y, and Z. So this is to combine different rules. And this rule is also called union. And the fifth rule here is called projectivity. It is used to separate one rule to multiple ones. So if X can determine Y and Z, the set of attributes Y and Z, X can be used to determine Y and Z separately. So these two rules are like doing the reverse operation of each other. The last one is pseudo transitivity. This one is a bit complex, but not that complex. So it is if X can determine Y and YZ can determine W, then XZ will also be able to determine W. So it's like we can if X determines Y, we can replace Y with X on the left hand side of other relations, of other rules. So this is the pseudo transitivity, and you may notice that the name of this rule is very similar to transitivity. It's called pseudo, so it is actually a shorthand for common transitivity, and we will show that why it is a shorthand later with an example. So here, actually this slide contains about 20 animations, and I messed up with 2 of them. But it doesn't affect what we will do now. We will do an exercise to practice the six rules we have learned. But we won't be practicing the first one, the reflexivity, because it's very simple. It's just it's very trivial. So let's do some rule, or let's derive some rules here. So assume we have a relation called R, which has 9 about I think is which has 10 attributes from A to J, and we have some existing functional dependencies here. AB can determine E, AG can determine J, BE can determine I, E can determine G, GI can determine H here. And let's try to derive something here. So first, AB can determine E, E can determine G. So what will AB give us here using the transitivity rule? G, yeah, of course, it's very straightforward. And if we use reflexivity here, sorry, it's actually I think it's project. If we use projectivity here, if we use projectivity, if we use, let's see, what? Let's say we just use reflexivity here with 1. What will it give us? I think I may messed up with some of the. Oh, sorry, it's okay. Let's try to practice this one. Did you see the answer just now? Yes or no? Yes. I messed up with some of the animation on this page. Sorry about that. But it's like AB can determine AB, of course, itself, because it's reflexivity. So one set of attributes can, of course, determine itself. And let's say we apply rule 4 on this projectivity. So AB can determine AB. So what can we get here with projectivity? B. Yes. Let's assume we just put AB can determine B here. So we can have AB to can determine A as well. So let's try to just keep the second one here. And I messed up with this again, but this is supposed to be this is supposed to be the answer here. So AB can also determine BE if we use additivity. So do you know why? Because if by combining 1 and 5, AB can determine B, AB can determine E, we can combine these two rules into one. AB can determine B, E, a union of B, E. So this is the sixth question here. What about this one here? So which rule can we apply to these two dependencies? E determines G, GI determines H. So which one of the 6 rules could be applied? Oh, that's fast, that's fast. Pseudo transitivity here. So what will give us, what will pseudo transitivity give us here? Yes, EI determines H. So pseudo transitivity is like if A can determine B, we can replace B on the left hand side of any other rules with the value with A. So this is pseudo transitivity. We can apply pseudo transitivity here, and we can get another dependency, which is EI determines H. And just now we talked about pseudo transitivity is a shorthand for transitivity. So why it is a shorthand for transitivity? So can we use transitivity to, can we use some other, the rest of the rules to derive the pseudo transitivity rule? Actually, we can do it step by step, and let me show you why it is just a shorthand for transitivity. So from E determines G and GI determines H, we can get EI determines H, and this is the pseudo transitivity. And let's do it step by step and see why. So let's first consider the value, the rule E determines G. So E determines G can give us EI determines GI using the augmentation rule. So we can add a value on both sides, and that value is I here. We can get EI determines GI using augmentation. And once we have EI determines GI, and we are also given GI determines H, EI determines GI, GI determines H, which rule can we apply here? Yes, transitivity. We can use transitivity here. So EI to GI is derived based on augmentation, and GI to H is given. So we can apply transitivity to get EI determines H. So in the end, we are starting from E to G, E determines G, and GI determines H to EI determines H. So that's why pseudo transitivity is a shorthand for transitivity. It's like doing the augmentation and transitivity within one rule. So that's why it is called a shorthand for transitivity. And that's all for today's lecture. And you will be using this today's content for, I think for your last quiz, and for your next quiz, you will be using PsychoPG tool. You'll be practicing that, and we will release the specifications for assignment 2 later this week. So stay updated. Okay, that's all. Thank you.